Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show CFD analysis through a chill beam using SolidWorks 2022. Actually, this chill beam is used in HVAC system in large buildings or commercial buildings, and these chill beams are used for both heating and cooling purpose. For understanding the geometry, let us have a segmented view of this model. For understanding the geometry, let us have a segmented view of this model. You can cut it from front plane. This is the geometry. So inside these tubes, we are providing water at lower temperature. Generally, temperature will be in the range of 10 to 15 degrees centigrade. And this one is the exit of cold water. And this cold water is surrounded with a lot of fins. The fins are made up of aluminum. So the thing is, from this cold water, it will be transferred to the fins. From backside, we will provide fresh air at room temperature, and it will be passing through this shell, and through the shell also we are having some kind of nozzles, and fresh air will be entering through these nozzles inside this container, right? So in this chill beam, what happens is actually we can have both heating and cooling effect. The central part of this one will be having heating effect, and the side part will be having cooling effect. Generally, in this type of chill beam, we can expect a temperature in the range of 15 to 20 degrees centigrade, right? So without wasting time, let us start our simulation. We need to start from Wizard, and flow simulation environment will be initiated with Wizard. Let us start with Wizard, and we're keeping the name on the project as project 2. We're considering unit as default unit system as SI, and temperature will be in degrees Celsius. Next to that, it will be internal analysis, and we're considering fluid flow with conduction, and definitely gravity will be involved. And along Y it will be minus 9.81 meter per second square. Along Z it will be 0. Next to that, we need to select gases or fluids. We're considering default fluid as air, and excluding that we need to select some liquid also, and we're considering liquid as water. Next to that, we need to select materials. In this case, we'll be considering only one material, and others will be provided during application of boundary conditions. Let us consider alloys. The material is made up of aluminum alloys, aluminum 6061 alloy, and the other materials will be provided during application of boundary conditions. Aluminum alloy will be considered for these fins. Next to that, default out-of-wall thermal conditions or roughness we're considering, and finally we need to select thermodynamic parameters. Pressure is 10132 Pascal, and room temperature is 30 degrees centigrade, and also solid parameters, it will be 30 degrees centigrade. Let us finish this. Now you can see this is the computational domain. It is an internal analysis, so we can hide this computational domain, and we need to apply our boundary conditions and fluid subdomains. Initially, for fluid subdomains, we need to have a segmented view of this model. Let us cut it from specific planes. Done. Another thing is, first of all, we need to provide water at lower temperature from these fluid subdomains. Insert fluid subdomains. It will be water at lower temperature, and from thermodynamic parameters we can select water. It will be at a temperature of 10 degrees centigrade. Generally, in this type of chill beams, temperature of water remains in the range of 10 to 15 degrees centigrade, but here in this case we are considering temperature as 10 degrees centigrade, right? We need to select that inlet location of these copper tubes. It will be from here itself. Select other, and we can select the specific lead location. This lead number 5 selected. This is the fluid subdomain, that is water domain at a temperature of 10 degrees centigrade, right? I'm going to check. Next to that, we need to select air, that is fresh air, that will be coming out from this location. Fluid subdomains, insert fluid subdomain, and it will be air at a temperature of 30 degrees centigrade. It will be coming out from here. Select. So this is the fluid subdomain of air. From this one, air will be passing out at a temperature of 30 degrees centigrade. right? Green check. Done. Two domains we have defined already. Next to that, we need to apply our solid materials. Insert solid materials. We're having three different types of materials in this case. Predefined alloys. We're considering aluminum 6061 alloys for the fins. You can select the fins from the geometry itself. Let us select it from here, from solid bodies. This is the starting of these fins. You can select. Next, we can select the last part of the fins. This is the last part. So all the fins are selected and it is made up of aluminum 6061 alloys. Green check. Next to that, we need to select other materials. Insert solid material, we need to select this steel for the casing. Predefined alloys, and it is steel. We're considering stainless steel 321, and let us select this one from here itself. This one, this part, and also the back part to be selected. Let us rotate this one a little bit to select the back part of this one. Done. Green check. It is made up of stainless steel 321. Next to that, we need to select copper materials. Again, solid materials, insert, and predefined. It will be metals. Under metals, it will be copper 1, and also by the same time, we need to select this copper tubes. Both the materials selected. Green check. So all the three different types of materials we have selected. Next, we need to apply our boundary conditions, right? Insert boundary conditions. And initially, we need to apply water from the small diacopter tubes at a specific rate. Let us provide inlet velocity. In this case, we're considering inlet velocity to be 2 meters per second from these copper tubes, right? And thermodynamic parameters, it will be definitely 10 degrees centigrade. To have the specific location, you can rotate it. We will provide water at a rate of 2 meters per second, and the temperature of that one will be 10 degrees centigrade, right? Select other, and you can select lead. Selected. Green check. So first boundary condition is applied. Next to that, we need to apply other boundary conditions. From here, we'll provide air at a rate of 30 meters per second, and that will be at a temperature of 30 degrees centigrade, which is room temperature. So again, insert boundary condition, air, definitely, because domains are already defined. From this location only air will be passing out. And let us consider the velocity of this one should be 30 meters per second. It will be also having temperature of 30 degrees centigrade, right? Apply this one. Two boundary conditions are applied, and again some other boundary conditions are needed. Let us rotate this one a little bit for applying these things. This is the exit of this pipe, so it will be exposed to atmosphere, so we can have pressure equal to atmospheric pressure at this location, right? So boundary conditions, insert boundary condition, and it will be equal to atmospheric pressure at this location. Select. Green check. Done. Again, we need to apply boundary conditions at the exit of these copper tubes, right? So for that, we need to have a complete view of this model. This is the complete model. Boundary conditions, insert boundary condition, and here at this location it will be equal to atmospheric pressure as it is the exit of cold water, right? Select other. This is lead number 1, and it will be having temperature of 10 degrees centigrade and pressure will be equal to atmospheric pressure. Green check. Done. Now the thing is, at the bottom also, from this one we need to apply another boundary condition that will be equal to atmospheric pressure at the down location, right? For that one, we can have a segmented view of this model. We can cut it from specific plane. Let us cut it from front plane. Green check. As this one will be exposed to atmosphere, so we can have a boundary condition at this location. boundary condition, insert boundary condition. It will be atmospheric pressure at this location. Selected, go and check. So we got 5 different boundary conditions, 2 inlet velocities and 3 atmospheric pressures, right? Next to that, we need to select some goals. We can have different types of goals, but our main aim is to have temperature at the different locations. Our main concern is the base plate. The exterior left hand and right hand of this chill beam will be having less temperature, and the middle one will be having higher temperature. So this chilled beam is having 2 types of temperature. Middle part will be having higher temperature. We can expect a temperature at the middle level to be in the order of 20 to 25 degrees centigrade, and the left hand side, which will be the cooler section, it will be having temperature in the range of 15 to 20 degrees centigrade approximately, right? So our goal should be to have temperature at different ranges, and also we need to find out temperature at the exit of these pipes, right? So let us select it. First of all, we select goals. It will be definitely surface goals, and it will be average temperature of fluid at left hand side of this one and right hand side of this one also, and we want to create separate goals for each of them. Go and check, and we can rename this one as, first one, it will be average temperature of air at left bottom entry. Done. Similarly, this one will be average temperature of air at the right bottom end. Done. Next to that, we need to have temperature at the central part of this bottom plate. So we can select another goal, insert surface goals, and it will be average temperature of fluid at the bottom surface of this one, right? Select, go and check, and we can rename this one as average temperature of air at the bottom central part. At central bottom part. Part of plate, same thing. Done. 3 different goals we have selected. Excluding that one, we need to find out the temperature at the exit of these pipes, right? For that, we need to have the complete view of this model. We need to have temperature at this location also. Goals, insert surface goals, and it will be average temperature of fluid definitely, and at this location select other, and it will be lead number 1. Green check, and we can rename this one as average temperature of cold water at exit. Next to that, we need to run it. So for running this simulation, it will take huge amount of time. For saving the time, we have already run this with the same data, and the result is already available in project 1. So let us view the result from project 1. And in this case, we got all the results converged. And for seeing the dynamics of flow particles and different cut plots, we need to make the model transparent. Let us make it transparent. So you can see the model is completely transparent. We can view the dynamics of flow particles and also the different cut plots of pressure and temperature through this chiller beam, right? So first of all, we need to select results from the project 1, because the simulation is done with the same data. We can select project 1, and we need to load results. First of all, we need to see results from cut plots, and it will be cut plot 1. Let us select cut plot, insert cut plots, and it will be temperature of fluid from this plane, right? Let us select this one. You can see this is the temperature distribution through this plane. It will be better to see this one from front plane, and we can expect this one in the form of an animation. That will be better for representation. Let us see this one in the form of an animation. You can see at the central part, temperature is in the range of 30 degrees centigrade, and at the bottom part, at this location, temperature of water is in the range of 10 degrees centigrade, and this symmetric both side, left hand side and right hand side, it is having similar type of temperature distribution. Our aim is to have temperature at this location, and also at the central part, right? You You see this distribution. Let us have a rotated view. We can expect this one from other plane also, from right plane also we can check it. Instead of temperature, you can view pressure also. Let us see pressure distribution from here. Actually, in this case, we don't find that much of difference in pressure. Let us view that one also. We can see pressure throughout this chilled beam is not that much of varying. It is almost same. Only pressure is varying inside these copper tubes. Initially, pressure is very high, and at the exit of this one, pressure is very less. We can expect this one from other plane also. Let us cut it from other plane and check it. Cut plot 1. Let us clear and hide, and we will see this one from right plane, right? Cut plot 2. Edit definition, and we want to see this one from right plane. You can select the plane from here, from the geometry itself, to from right plane, and we want to see temperature distribution, temperature of fluid from right plane. Let us see it. We want to view this from right side also. See, it will be better to see in the form of an animation. Let us see the animation of this one from right plane. You see bottom side temperature is very less and top side temperature is high. It is in the range of 30 degrees centigrade, and as it is coming down, temperature is decreasing, and through the fins actually huge amount of heat transfer is occurring, right? Let us clear and hide this. Cut plot 2, clear and hide. Next to that, we need to see surface plots. Before that, we need to see the model in isometric view, model in isometric formation, right? Okay, now surface plots, insert surface plots, and we want to see temperature throughout the surface of this chill beam, and we need to select all surfaces, green check. You can see temperature distribution at different surfaces. It is different. Through the big pipe, it is in the range of 30 degrees centigrade, and through the copper tubes downside, its temperature is in the range of 10 to 12 degrees centigrade, and at the outer periphery of this chill beam, we're having different ranges of temperature, but both the ranges of temperature are symmetric. You can see this side and the other side. You can rotate this and see both sides the temperature distribution is completely symmetric. Okay, right. This one clear and hide this surface plots. We want to clear and hide these surface plots. Next to that, we want to see very important thing, that is dynamics of flow particles, how the particles will be flowing from one end to other end throughout this chilled beam, right? So flow trajectories, and for that one, initially we'll make the model with a segmented view. We can cut it from right plane, and we'll see dynamics of flow particles. So insert flow trajectories, and we'll see 200 numbers of particles will be moving from this location through the pipes, and also it will be moving throughout these locations. We can rotate this one to have different locations of this one. Done. So through these different surfaces, we want to see dynamics of flow particles, right? Green check. Now we want to see the dynamics of flow particles in the form of an animation. Let us play the flow particles. We want to see from both the sides. Let us see from front plane first. You can see how the flow particles are moving throughout this chilled beam. At the inner part, we can see temperature distribution. It is in the blue range, which is in the range of 10 to 12 degrees centigrade, and the top side, it is in the range of 28 to 30 degrees centigrade, and inside this one at the middle, it is in the range of 23 to 25 degrees centigrade. As these air particles are coming down, its temperature is decreasing, right? And can see at the two different locations, left hand side and right hand side, its temperature is in the range of 14 to 16 degrees centigrade. And the central part, its temperature is a little bit higher. It is approximately in the range of 90 to 20 degrees centigrade approximately. We'll see all these temperatures from gold plots also, right? Let us change the pattern of these flow particles and we'll see in a different way. Clear and hide, and you want to see these things in a different way, right? So edit definition, and instead of these things we can see in the form of different way. Let us make the flow particles with the size of 10 millimeter. Let us view it. So this is the dynamics of flow particles. We can have it in the form of animation. It is clearly evident that at different locations we are having different temperatures as indicated by different colors. Blue color is actually in the range of 10 to 15 degrees centigrade, and red is in the range of 30 degrees centigrade. In between we are having different ranges, like green and yellow, all different ranges are there, right? You can have an isometric view of this model. See how these flow particles are moving. This part is not transparent actually. We could not make it transparent. Let us make it hidden. Then you can see in a better way. Actually this chilled beam is working as a heating and cooling device. At the central part or the base part, its temperature will be approximately 20 degrees centigrade, and the extreme left hand side and right hand side of the bottom part, temperature in the range of 15 to 16 degrees centigrade approximately. We'll see all these things from the gold plots also, right? Let us close it. Clear and hide. And next to that we need to see our gold plots. Insert gold plots, and we want to see all the goals, because we decided to have 4 different goals: temperature at the 3 different surfaces, at the central part and the 2 left hand side and right hand side part. By the same time we want to have temperature at the exit of this cold water. And better to have all these things in the form of Excel, or we can see from here itself also. Let us see it from Excel by exporting it to Excel. Let us see this one. So this one showing average temperature of air at the central base part. You can see initially average temperature of central part was 30 degrees centigrade, and after 395 numbers of iterations its temperature has come down. Its temperature is in the range of 20.148 degrees centigrade. So the central part is having a little bit of higher temperature compared to the sideways, because sideways actually we got different temperatures. Next to that we can see the second one, which is average temperature of air at the right side base plate. Initially its temperature was 30 degrees centigrade, and after 396 numbers of iterations its temperature has come down. It is in the range of 14.498 degrees Celsius. And next one, it is average temperature of air at the left side of the base plate. Again you can see here it is in the range of 14.128 degrees centigrade. So we can see that generally in the left hand side and right hand side we are having temperature in the range of 14 degrees centigrade, and the central part, which is having temperature in the range of 20 degrees centigrade. Same base plate we are having different temperature zones. At the middle part we are having temperature 20 degrees centigrade, and at the extreme left hand side and right hand side we are having temperature in the range of 14 degrees centigrade. And finally we can see the temperature at the exit of cold water. Initially cold water was in the range of 10 degrees centigrade, and finally after 396 numbers of iterations its temperature has risen a very little amount. It is 10.028 degrees centigrade. Now we can see all these temperature ranges and these graphs in the same plot that can be viewed from here itself. Let us see all these results from here, and you can view all these results in the form of graph also from here. History, right? What we have seen before. First one is average temperature of water at pipe exit. It is in the range of 10.028 degrees centigrade here. Second one is average temperature of air at the left side of the base plate. It is 14.165 degrees centigrade. Next one, it is average temperature of air at the right side of the base plate. It is in the range of 14.50 degrees centigrade. And finally, the last one is average temperature of air at the central base part or central base plate. It is in the range of approximately 20 degrees centigrade, right? Excluding that one, you can go for some kind of parametric study, because the thing is, in parametric study, you can vary the input variables and see the temperature differences at different locations. The input variables may be the mass flow rate or velocity of this cold water, or we can do one thing, we can change the orientation of these injectors. At this location, the injector are having angle in between them equal to 100 degrees. Those two are actually pointing towards the extreme left hand side and right hand side. If you want to vary the temperature at the extreme right hand side and right hand side plates, the orientation of these injectors can be varied also. And with that variation, we can go for the different types of parametric studies. In this type of parametric study, today at this moment, we'll change the mass flow rate of this cold water and see what are the different values available. We have already conducted a parametric study with different mass flow rates. Let us see that one. Right? We have already conducted a design of experiments and optimization. We have considered velocity of cold water in the range of 0.1 to 5 meter per second. Let us see the results from here. You can see that when velocity of cold water is increasing, you can see the temperature at the base plate, left hand side and right hand side, actually it is decreasing. When velocity is 0.1 meter per second, you can see the temperature at the base plate, left hand side is 16.14 degrees centigrade and right hand side is 15.99 degrees centigrade. And in all cases, the temperature at the exit of cold water remains almost same. Whatever the velocity of cold water through these copper tubes, if it is increasing from 0.1 to 5 meter per second, in almost all cases, the temperature at the exit of these copper tubes remains almost constant. It is decreasing very little amount. Initially, it was 10.49, and when the velocity of cold water was 5 meter per second, it is temperature at the exit location is 10.01 degrees centigrade. And our aim is to see the temperature at the central part and also temperature at the sidewise locations at the extreme left hand side and right hand side. We can see the temperature at the central part is always almost constant. If we are increasing the velocity of this cold water, you can see there is a very little decrease in temperature at the central part. So initially temperature of central part was 20.83 degrees centigrade when velocity of cold water was 0.1 meter per second, and when the velocity of cold water is 5 meter per second, you can see the temperature at the central part is 20.31 degrees centigrade. That means we can say that temperature at the central part remains almost constant in the range of 20 degrees centigrade. But the thing is, as we are increasing the mass flow rate or velocity of cold water from these copper tubes, you can see there is a decrease in temperature of the plates at the left hand side and right hand side. So to have more efficiency or to have more decrease in temperature at the sideways, we need to have more mass flow rate or more velocity of cold water, right? You can see here when the velocity was 0.1 meter per second, the average temperature at the side plates is approximately 16 degrees centigrade, and when the velocity of cold water is 0.5 meter per second, in that case temperature at the sidewise plates equal to 14.5 degrees centigrade approximately, and when velocity is 1 meter per second, in that case temperature is again approximately 14.4 degrees centigrade, and when velocity is 3 meter per second, in that case you can see temperature is 14.2 degrees centigrade, and when velocity is 5 meter per second, in that case you can see temperature is 14.19 degrees centigrade. So we can see here, to decrease the temperature of side plates, we need to feed cold water at a higher rate, right? So instead of stopping it here, we can go for further optimization. That means if you want to have a specific temperature at a specific zone, whether it is in the central part of this plate or it may be at the sideways of the plate, we can have some idea from this parametric study, and based on that idea we can narrow this gap and have a specific goal with a specific temperature. Okay, so With this one, we will conclude our today's analysis. This is a very simple analysis of a chill beam, which is utilized in high-rise buildings or commercial buildings. And in this type of chill beams, we can have both heating and cooling effects. Okay. So with this one, we can conclude our analysis. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.